Hi everyone. So in the previous video we have studied the basics of OpAmp, then we studied OpAmp as a comparator, then we studied the concept of virtual short. And there in the last lecture, in the end I told you, I will tell you why it is called virtual short. What is the meaning of that word virtual? So that I will tell you in this lecture. So in this lecture we are going to see the different configuration of OpAmp in negative feedback. Why in negative feedback? Because in the negative feedback the concept of virtual short is valid. So we are going to see the configuration in negative feedback only. So first we are going to see non-inverting amplifier. Why it is called non-inverting amplifier? Because here the input is connected to non-inverting terminal. This terminal is non-inverting, this terminal is inverting. So input is connected to non-inverting terminal. That's why it is called non-inverting amplifier. And when you see the output of this, we will calculate the voltage gain. So when you see the output, you will realize why it is called non-inverting again. Because in the output you will see there is 0 degree phase shift between output and input. So once we calculate the voltage gain, you will see that. So this is the configuration given. OpAmp is given, then there is a feedback resistance, there is this input voltage, and then there is a output voltage. So we need to calculate three things. We will calculate voltage gain, V naught by V in. We will calculate input resistance, we will calculate output resistance. So let's start one by one. Let's calculate the voltage gain first. And what we are considering? We are considering ideal OpAmp. What do you mean by ideal OpAmp? That Rin is infinity. Rin is infinity. That means the current here is 0 ampere. The current here is 0 ampere. What else do you consider? If ideal OpAmp is there, that means this gain is infinity. Well and good. And if it is ideal OpAmp and then there is a negative feedback. Why it is negative feedback? Why there is a negative feedback? Because if this node increases, then what will happen? This node will increase. And if negative node is increasing, that means certainly this node is decreasing. Are you getting this point? If V node is increases, then this node increase. I told you when we were studying the basics in the very first page, what did I tell you? That if negative node increases, then V naught would decrease. So same thing is happening here. V naught increases, then this node increases. If this node increases, then this decreases. That means there is a negative feedback. So if there is negative feedback, you can apply the concept of virtual short. So this is what we are going to do. So first we are calculating voltage gain. This is your V in. What do you mean by concept of virtual short? The potential of non-inverting terminal will be equal to the potential of inverting terminal, right? So what is the non-inverting terminal? This is the non-inverting terminal, this is the inverting terminal. So potential of inverting terminal will be equal to the non-inverting terminal. So this potential will be equal to Vi only. If this potential is Vi, tell me how much current is flowing here? Vi by R. Say yes or no. If this potential is Vi by R current is flowing because that is grounded. Now there is zero current here, right? Zero current inside. 0 ampere current. That means the same Vi by R current is flowing through RF as well. Say yes or no. V in. So Vi by R current is flowing. That same current is flowing through RF as well because there is no input current in the OpAmp. Say yes or no. Well and good. Now, if V in by RF current is flowing, then what is the voltage drop here? In this direction, there will be a voltage drop that will be V in by R into RF. Say yes or no. The voltage drop is V in by R current into resistance in this direction. Now tell me what is your V naught? V naught will be this potential, that is V in, plus this potential V in by R plus RF. V in by R into RF. This is your V naught. Say yes or no. Did you understand this point or not? Now I will tell you why the concept was called virtual short. So what did I do here? I applied V in potential, right? This potential is same as V in only. Now one can have this doubt, sir, that sir, this V in by R current is flowing through RF, that is for sure. But why this current cannot flow through V in as well? Because this is also a node, no? V in is also a node. Why this current cannot flow through V in? The current is not going into OpAmp, that's for sure. Some current will flow through RF, that is also for sure. But if there is a V in battery connected, why this current is not flowing through V in? Yeah, that is why it is called virtual. This is virtually shorted. It's not that there is some node. No. It's not that I am connecting a V in battery here. The V in battery is connected here only. This is virtually shorted. The potential of this node is V in. It's not that there is a battery, so that will drive some current. No, battery is not driving any current here. So that's why the word virtual is there. That it is virtually shorted. These two nodes are same, but virtually. These are virtually shorted. Okay, so that's why we say it is virtual short, and whatever the node is there, that will not drive any current. If it was grounded as well, it's not that the V in by R current would flow through ground. No. V in by R will not flow through the ground. The ground will not take any current. If it was grounded, let's just say if this node was grounded, then this node would also have been grounded. But it's not that the ground will take up any current. No, ground will not take up any current. Are you getting this point? So similarly, V in will not take up any current. It is just the potential of that particular node. The potential of that particular node is V in. That's why it is called virtual short. Both inverting and non-inverting terminal, both inverting terminal and non-inverting terminal are virtually shorted, not exactly shorted. They are not actually shorted, they are virtually shorted. Say yes or no. Understood? Okay, so this V in potential was there, V in by R current was there, that same current was flowing through RF. So what is the V node potential? V node potential is V in plus V in by R into RF. That is V node potential. So what you can write? 1 plus RF by R V in. So what is your V node by V in? So from here you can see V node by V in is 1 plus RF by R. So what do you see here is that there is 0 degree phase shift. There is 0 degree phase shift between output and input. That's why it is called non-inverting amplifier. So gain of non-inverting amplifier. Gain of non-inverting amplifier. So what did you understand? From here to here, from here to here, there is 0 degree phase shift. 0 degree phase shift. This is a good point that you can remember. So what is the gain of non-inverting amplifier? That is 1 plus RF by R, but in case of ideal op-amp, 1 plus RF by R. This you can remember as well. Okay, but once you have enough practice, we will solve a lot of configuration, we will solve a lot of problem, you will be eventually remembering it. So for now you don't need to mug it up. What you will see, okay, V in is connected at positive terminal, RF and R is the resistance, RF is the feedback resistance, this is the R, so 1 plus RF by R. Why it is feedback resistance, that we will see when we in that later on in this section only we will see why it is called feedback resistance. If you have studied feedback topology, then you would have certainly understood why it is called feedback resistance, right? So 1 plus R by R, that is the gain. What will be the input resistance? Tell me by your own. What should be the input resistance? What will be the input resistance? R in would be V in by I in, whatever the current that is flowing through V in. So what is the current flowing through V in? That is equals to 0 ampere, because I in is 0. In case of ideal, I in is 0. So V in by 0. So R in would be infinity. Well and good. What about R naught? What about R naught? If you are calculating R naught, if you are calculating output resistance, what you will do? You will nullify the effect of independent sources. Nullify the effect of independent sources. That means input V in will be gone. If this is gone, that means this node is 0. If this node is 0, this node is 0 and this node is 0. Both nodes are 0. That means there is 0 ampere current here. Now the same current will be flowing through RF as well. 0 ampere current is flowing. So now this 0 will travel and will reach here. So V naught is simply equals to 0 only. So what is your R naught? R naught is V naught by I naught. But here you can see that since input is gone, if input is gone, this node is also 0. Input, this node is grounded, this node is also grounded. If this node is grounded, that means there is 0 ampere current, the same current is flowing through RF. So V naught will be 0 only. So V naught is 0 by I naught. So R naught is simply becoming to be 0. So these are the three parameters: voltage gain, input resistance and output resistance. Well and good. Let's try finding out the same parameter, but now we are considering non-ideal case. So our op-amp has input resistance, it has a gain as well, finite gain, and it has a finite output resistance as well. So how will you make the circuit? How will the circuit look like? This is a resistance R. This node is grounded. Here there is RF. Here there is, this is your R in. This node is V in. This is R in. Let's just say this is VD. Now that will be amplified with the factor of A, because it has a gain of A. So A into VD you will get here, and then there is R naught. And this node is V naught, which is connected to finally RF. This is our R naught. This is your V naught. This is your RF. Say yes or no. Okay, so this is RF, R naught. Everything is crystal clear? Well and good, right? So this is how we will represent it. So this box, black box, is represented by this R in, AVD and R naught. Now we will calculate all the parameters. So first we will calculate voltage gain. So first we will calculate voltage gain. Now look one thing. See, if you are going to consider R naught and R in as well, then your voltage gain will be very complex. Are you getting this point? If I am going to consider R in and R naught, both of them, then voltage gain will be very complex. So when I am finding input resistance, I am only going to consider R in. When I am finding output resistance, I am only going to consider R out. When I am finding gain, so I am only going to consider A for the ease of calculation. And certainly in the examination, you will not find that your expression is written in terms of R in and R naught. Certainly, that is my guarantee. And even if the interviewer is asking you, he would expect that you take R in to be infinity and R naught to be 0. So assumption you have to take. If you are finding the voltage gain, in this case, you have to take the assumption that what will be the assumption? It's not that you will take R in to be 0, because the OpAmp input impedance is generally high. So you will take R in to be infinity and R naught to be 0. So always you need to take the assumption that your R in is for OpAmp. What is the scene? R in is typically high and R naught is typically low. So what is the assumption we are taking? So assuming R in to be infinity and R naught to be 0. So what will happen? This node will be simply grounded, right? And this R naught is infinite, R in is infinity. So that is also gone, right? This node was your VD. Well and good. So what is your V naught? Your V naught is simply A into VD. And if I say what is your VD? VD is V in minus, let's just call this potential as V. V in minus V. V in minus V. Now tell me what will be V? What V will be? This is our first equation. V naught is equals to AVD. AVD is AV in minus V. What will be V? So V will simply be, you can apply nodal analysis as well, or you can simply see this is a potential divider from V naught to towards R. This is simply a potential divider. So what will be V? V will be V naught into R upon R plus RF. Isn't it a simple potential divider? This is grounded. Then there is a resistance R. Then there is RF. Then there is V naught. This is RF. This is R. And you are finding the potential of this point, that is V. So V is R upon R plus RF into V naught. So this is equation 2. Now by equation 1 and 2, what do you see? V naught is equals to A V in minus, what is V? Let's just call this R upon R plus RF as beta. Okay, we are calling R upon RF as beta. So I will call this as equation 2, where beta is R upon R plus RF. This is your beta. So V will be replaced with beta V naught. So what you will get? V naught into 1 plus A beta, A V in. So V naught would be A upon 1 plus A beta V in. V naught by V in would be this. And what is beta here? Where beta is R upon R plus RF, right? R upon R plus RF. So this is the gain. And if A is very large, or you can say infinity, then what will happen? V naught by V in would be equals to A upon, if A is very large, that means this factor will be very large than A. So you can simply replace this value by 1 plus A beta. This can be replaced with A beta only, because this value is very larger, right? So it will be replaced with A beta only, because 1 will be very negligible. So your answer will be nearly approximate to 1 by beta. So what will be 1 by beta? 1 by beta will be reciprocal of this, R plus RF upon R, and that would be equals to 1 plus RF by R. So your V naught by V in is becoming 1 plus RF by R. Did you find the same expression for A equals to infinity? For A equals to infinity, did we find the same expression for A equals to infinity? What was the voltage gain? 1 plus RF by R when A was infinity. Are we finding the same expression? Yes, we have found the same expression, 1 plus RF by R. Say yes or no. Crystal clear? Everything is crystal clear? So this is the voltage gain. This is just to check. Okay, so this was the first thing. Let's just find the, what is the second thing that we need to find? Let's find the input resistance. This was A, second is B. If I am finding the input resistance, what is the assumption I am going to take? The assumption I am going to take is that your R naught is 0, because I don't want R naught in my final answer, right? I am finding input resistance. So my target is to find, this is your V in, you get I in out of it, right? So input resistance, this I am calling R in with feedback. Should I call it R in with feedback? Because if I call it R in, then the same name is there, no? R in. So I cannot call it R in. So I am calling it R in with feedback. So this is what I need to find, and that is V in by I in. This is V in by I in. So this is what I need to find, V in by I in. So if I am finding V in by I in, I need to know the potential here, right? I need to know the potential here. If I know the potential here, then that is very easy for me. If I know the potential at this point, that will be very easy for me. What will be the potential at this point? Since Rin is very large, already Rin is very large, I can apply the concept of potential divider. That would, this node will be beta V naught. I know this will not be completely beta V naught. Why it will not be completely beta V naught? Because Rin will also drive some current, but that is the assumption we are taking, because Rin is very large and R is very smaller than Rin. So we are considering all the current will be flowing through R only. So what I am considering, whatever the current coming here, there will be very less current coming here, all the current will be coming here only. So if this current was Ix, so complete Ix is flowing through R only. There is zero current going into Rin. Now you will say, sir, if there is zero current going into Rin, that means In is zero, so Rin is infinity. Yeah, your like calculation is correct, but we need to find the expression that will be very large. Rin with feedback, the final answer that we get, that will be very large, that's for sure. But we have to take an assumption to make our calculation easier. I am assuming that there is very less current coming. It's not that there is zero ampere current coming. There is very less current coming. So what will be the potential of this node? I can simply apply the concept of a potential divider. But for applying the concept of potential divider, the thing is this should drive 0 ampere current. Then only you can apply the concept of potential divider. So yeah, I am assuming that it is driving very less current. So I am applying the concept of potential divider here. So these are the assumptions that we have to make our calculation easier. So this node will simply be beta V naught only. So what I can write is that from here, V in minus beta V naught divided by R in is equals to I in. Say yes or no. Right? Now what is your V naught? What is your V naught? So before writing V naught, I can write this I in into R in. By the previous analysis, here I found out the value of V naught. V naught was A upon 1 plus A beta into V in. V naught was A upon 1 plus A beta into V in. That would be I in into R in. Say yes or no. there is something certainly wrong. V in minus beta V naught. V in minus beta V naught upon R in is equals to I in R in, I in R in. V in is, no, nothing is wrong, just so 1 minus A beta upon 1 plus A beta you understood, right? I took the, let's just call, I just took the common V in, I am taking common, so V in I am taking common, so 1 minus A beta upon 1 plus A beta is equals to I in R in, right? So what will be the value of R in? V in by I in, that is your R in with feedback, R in with feedback, that is coming out to be R in into 1 plus A beta. So this is your expression. Now A is already very large, beta is also a finite value, so this value is going to be actually very large only. This is near to infinity only, but still we took the assumption and then we calculated our final answer. So what was the scene that what we did? We need V in by I in, that I know. I need V in by I in. So what is my V in by I? What is my R in value? That is simply V in minus this potential. This potential I am assuming to be beta V naught directly. What is beta V naught? What is beta? Beta is R upon R plus RF. Beta is R upon R plus RF. So this potential I am directly assuming to be beta V naught. So V in minus beta V naught divided by R in is equals to I in. Now I just need to replace this V naught by V in. So in the previous expression, here I calculated what is my V naught. V naught is A upon 1 plus A beta. So V naught is A upon 1 plus A beta into V in. So from here I calculated my final answer, that is coming to be R in into 1 plus A beta. So this is my final answer. Say yes or no. So this is my input resistance. If A is very large, or tending to infinity, then what will be your R in with feedback? What will be your R in with feedback? If A is very large, if this value is very large, this is infinity, then completely it will be infinity only. So R in with feedback will be infinity only. So what did I calculate when I was considering ideal case? So when I was considering ideal case, my input resistance was coming up to be infinity only. The same thing is happening here. Input resistance is infinity only. Now what about R naught? So now we are going to calculate R naught. So let me add a page. Now the third thing I am going to calculate is R naught, output impedance. For calculating R naught, what is the first thing I am going to do? I am going to short circuit the input. The input is shorted. This is the first thing I am going to do. Input is gone, right? This node is gone. What will be the potential of this node? Potential of this node, again I am considering beta V naught, because I am considering that there is very less current going into R in, right? There is very less current going into R in, so I can simply apply the concept of potential divider. So this node is beta V naught. This is what I am considering. So what this value will be? Can you tell me what will be this value? A into VD. What is VD? VD is 0 minus beta V naught. VD is, this node is 0 minus beta V naught. Say yes or no. So it will be minus A beta V naught, right? Now I need to calculate R naught. So from here I need to calculate the R naught. So what I will do, I will apply V naught and get I naught out of it. Now there will be one more assumption. Okay, so this is how we calculate the answers. There is no other way. If you are taking the complete cases, if you are going to consider all of the things, then your expression will be very complex and that will be of no use. So one more assumption I will take. What is that assumption? That this I naught current. Now I know one thing, this R naught is very low, right? This R naught is very low. So the assumption I am going to make is that this complete I naught is flowing through R naught only. When we were studying feedback topology, there also we took these kind of assumptions. I have V naught, I have I naught current. This I naught current has two paths. It can go from RF as well, it can go from R naught as well. But since your R naught is very low, so the complete I naught will be flowing through R naught only. Say yes or no. Did you understand this concept or no? Now you will say, sir, in RF as well there will be current that would be V in minus beta V naught divided by RF. Yeah, there will be current, I know. The current will be V naught minus beta V naught divided by RF. There will be current, but that is the assumption I am taking. No, that current is very low. I am considering V naught minus beta V naught divided by RF current is very low. This is the assumption that I am making. So the assumption that I have made is that the complete current is flowing through R naught. The complete I naught current that is coming, that is flowing through R naught only. So this is the assumption that I am making. So based on the assumption we are doing our calculation. So complete I naught is flowing through R naught. So what you can write now? You can write that V naught, this node is V naught minus this node. What is this node? This node is minus of A beta V naught divided by R naught is equals to I naught. So what will be your V naught by I naught? That would be R naught upon 1 plus A beta. That's it. So what was your R naught? I should call it R naught with feedback. So R naught with feedback is V naught by I naught. R naught with feedback is V naught by I naught. This is what I needed to calculate, and this is what I have calculated here. R naught with feedback, that is R naught upon 1 plus A beta. R naught upon 1 plus A beta. Right? So, and also if here I can write, if A is infinity, if A is tending to infinity, or if A is very large, what will happen? This value will be infinity. So what you will get? R naught F. If A is lower value is infinity, then what you will get? R naught F will be equals to 0 only. And this is what you got previously when we calculated it for ideal case. R naught was 0 only. So till now what we have studied, we are studying about non-inverting amplifier. So first we saw the ideal case. In ideal case, there is input current is 0, Rn is infinity, R naught is 0, and there is the gain is also infinity. So you can simply apply the concept of virtual short. You applied the concept of virtual short, you got the value of V naught, that is 1 plus Rf by R. Also we got to know that from here to here there is 0 degree phase shift. Well and good, no doubt there, right? Then we calculated input resistance. If the current is 0, then simply the input resistance is infinity. Then calculated output resistance. So in output resistance, you have to short circuit the input. So 0 is going there. So there is 0 ampere current. So through RF as well, there is 0 ampere current. So this V naught will be traveling to simply output. What was happening? There was 0 voltage drop. So 0 is coming to output. So R naught is 0. Right? Now talking about non-ideal case now. You have Rin, you have A, you have R naught. But we have to take again assumptions. If I am calculating the voltage gain, I am considering R naught is 0 and Rin is infinity. So from V naught, there is beta V naught coming here. So directly you can write A is, V naught is equals to A into V in minus beta V naught. V naught is equals to A into V in minus beta V naught. So from there I got A upon 1 plus A beta. If I put A is very large, then I will get 1 by beta, that is equals to 1 plus RF by R only, which was the gain in the previous case. Then I calculated the input resistance. For calculating the input resistance, again the assumption I am taking is that through Rin there is very less current, so I can apply the concept of potential divider. So the node V negative node is beta V naught now. So if V negative node is beta V naught, so A into V in minus beta V naught is equals to V naught. From there I could replace the value of V naught, that is equals to A upon 1 plus A beta into V in. Then from there I calculated my input resistance, that is Rin into 1 plus A beta. Then I calculated the output resistance in the similar manner. The assumption that I took is the I naught current is completely flowing through R naught only, because R naught is already very low. So R naught, so output resistance I was getting is R naught upon 1 plus A beta. Well and good. Now all these things you don't even need to do in the examination if you have studied the concept of feedback topology and feedback amplifier. So now we are going to understand the feedback topology of this non-inverting amplifier. So what kind of feedback topology is there? Tell me. What kind of feedback topology is there? Is there current mixing? No, there is no current mixing, because input current has only one path. Input current has to go like this. So there is certainly voltage mixing. And for sampling, what is the method I told you? For sampling, you just need to put V naught equals to 0. If you put V naught equals to 0, is there any part coming here? If your V naught is 0, there will be nothing coming here. So certainly there is voltage sampling. But forget about these shortcut methods. If I do by concept, if I go by concept, this was just a shortcut method. If I go by concept, what will happen? This is V naught. So here there will be some part coming, that would be beta V naught, where considering beta is R upon R plus RF. So from output some part is coming here, that is beta V naught, and that is being mixed with the input. So V in minus beta V naught, V in minus beta V naught is fed to the amplifier, of gain A, and you are getting your final output. So this is what is happening. So from output voltage is being sampled. From output this voltage is being sampled and it is mixed with the input voltage only. So there is voltage mixing and voltage sampling. Say yes or no. So what kind of feedback topology is there? So sampling is voltage and mixing is voltage. So voltage feedback topology. And if it is voltage feedback topology, then what kind of amplifier is that? It is a voltage amplifier. Voltage amplifier. So if I draw a rough diagram of it, what will happen? So what was happening? Your input was coming. This was your V in. You had a V in. And you had a gain of A. This was the voltage gain. Voltage gain of A. Then you received some output. And from output, you fed back some part to the input. You fed back some part to the input. Look, this was your output. You fed back some part to the input. In case of negative, with the case of negative feedback. That was R upon R plus RF. This is your V naught. So you fed it back. And it got subtracted. It got subtracted. This part was fed, that was R upon R plus RF into V naught. So V in minus this part was subtracted, then you got some potential here that was multiplied with the factor of A and you got V naught output. So this is the basic block diagram of what is happening in this circuit. There is a forward gain. From output there is a feedback factor that is being fed, then there is an input V in minus beta V naught. Everything is crystal clear. You can relate this diagram to this one, right? What kind of feedback topology is there? Voltage feedback topology. For voltage feedback topology, what is the scene? I will write it in a better manner. Voltage feedback topology. So for voltage feedback topology, it is a voltage amplifier, right? Input resistance is higher or lower? For a voltage amplifier, you need input resistance to be high so that more and more voltage coming across the input resistance. So you need Rin to be high and R0 to be low so that more and more voltage goes towards the load, not across the R0. You want your R0 to be low, right? So what do you think? What will be your Rin? Rin with feedback. You want your Rin to be high, so it would be Rin into 1 plus A beta. If you want it to be high, and if you want it to be low, that means this factor should come in the denominator. If this is being multiplied, that means it is increasing. If it is coming into the denominator, that means it is decreasing. So this is how you can write Rin. This is how you can directly write R0. And what about voltage gain? Voltage gain. So in negative feedback, we know what is the gain. The gain is A upon 1 plus A beta. That's it. So without doing any calculation, just by the concept of feedback topology, we have jotted down all the answers. Say yes or no. What is this A? A is the voltage gain. A is always the voltage gain. the operational amplifier is a voltage amplifier only. The operational amplifier is voltage amplifier only. Now in this operational amplifier you applied a Vin input directly and then you got some output. But it's not necessary that this complete configuration will be acting as a voltage amplifier. Look, what did I say? This is a voltage amplifier, but it's not necessary that the complete configuration should act as voltage amplifier. In this case, it is acting as voltage amplifier. Now we are going to study inverting amplifier. In inverting amplifier, the complete configuration will not act as voltage amplifier. It will act as transresistance amplifier. So we will see about this case now. Now we are going to study inverting amplifier. Okay. So what did I say? That this configuration is voltage amplifier, but it's not necessary that this complete configuration will be a voltage amplifier. It can be any other amplifier as well. It can be transresistance, it can be transconductance, it can be current amplifier as well. Are you getting this point? So here it was the case of voltage amplifier. So voltage amplifier, we know all those things. Voltage gain A upon 1 plus A beta, input resistance we know, output resistance we know, everything we calculated. We calculated for ideal case as well, non-ideal case as well. The same kind of analysis we are going to do for inverting amplifier now. So why it is called inverting amplifier? Because input is applied at inverting terminal. This is the inverting terminal. So input is applied at inverting terminal. So that's why it is called inverting amplifier. Why it is called inverting amplifier? Because input is applied at inverting terminal. And now you will see the voltage gain. There also you will realize why it is called inverting amplifier. So how will you find the voltage gain? Considering ideal op-amp. Considering what? Ideal op-amp. So you see, so if it is ideal op-amp, so if this node is 0, this node will also be 0. If this node is 0, this node will also be 0. So at 0 node, at this node you can apply the nodal. So how will you apply the nodal? Or without even applying the nodal, you can also write. What you will do? If this is 0, this node is also 0. So what is the current here? V in by R. Right? Now if this node is 0, it doesn't mean that V in by R current will be flowing here. No. V in by R current will not be flowing here. Because this is a virtual source. The only thing is the potential of this node is 0. It's not that it is ground. So this V in by R current will be flowing through, this V in by R will be flowing through this RF. So in this RF, there will be V in by R current. So in this RF, V in by R current is flowing. So if in this direction V in by R current is flowing, then what is the voltage drop? Voltage drop is V in by R into RF. What will be your V naught? 0 minus V naught. This potential is 0. 0 minus this potential is equals to V naught. Are you getting this point? This node is 0. 0 minus this potential. What is this potential? V in by R into RF. So minus V in by R into RF is equals to V naught. So V naught by V in is minus RF by R. That's it. So this is the voltage gain. And what did you realize? That there is 180-degree phase shift between input and output. So from here to here, there is 180-degree phase shift. From here to here, there is 180-degree phase shift. V in by R current is flowing, that is flowing through RF. So 0 minus V in by R into RF is equals to V naught. So V naught by V in is minus RF by R. Say yes or no. Understood? Well and good. Everything is crystal clear. Now we are going to calculate input resistance. For calculating input resistance, what you need to do? You need to calculate V in by I in. So what is your input resistance? That is V in by I in. Tell me, what is the value of V in by I in? This is what you need to calculate. Concept of virtual short is again valid because this is a negative feedback. Yeah, why it is negative feedback? Again you can check. This node is increasing. Then what will happen? This node will also increase. Because this is for checking negative feedback, what do we do? First we short circuit the input. We nullify the effect of input. What is our input? That is voltage source. That will be shorted. So if this node increases, then this node will increase. Because this is simply potential divider only. If this node increases, that means this node will decrease. That's it. If this node increases, this node will increase because this is a potential divider. It is a simple potential divider. From here, it is a potential divider. If this node increases, that means this node will increase from this path. This node will increase. And if this node increases, that means this node will decrease. That's it. Understood? Right. So this is a negative feedback that you can see. Also, you can see that there is a feedback connected to negative terminal. So there is a negative feedback only. This node increases. Why this node? If this node increases, why this node increases? Because of the feedback path. Because of the feedback path. The feedback path is This is the feedback path. So this is a simple potential divider. So if this node increases, then this node will increase. But if this node is increasing, that means this node will decrease, right? Okay, yeah. So since it is in negative feedback, the virtual short is valid. So this node is 0. So V in by R is equals to I in. Say yes or no. V in by R is equals to I in. So V in by I in. So V in by I in, that is equals to R in, that is equals to R. That's it. So what is the input resistance you are getting? That is equals to R only. So input resistance is R. Well and good. What is the input resistance? Input resistance is R. V in by I in is equals to R only. What is the output resistance? For calculating output resistance, what is the first thing to do? This will be shorted. This is already shorted. If this is shorted, this node is also 0, this node is also 0. What is the current here? 0 ampere. The same 0 ampere current is flowing through this RF as well. This is also 0 ampere. If there is 0 ampere, that means here there is 0 voltage drop. So this is 0 volt, this is 0 volt drop. So V0 will be 0 only, right? So what was your R0? R0 was V0 by I0. Your V0 is 0. So 0 by I0, that will be 0 only. So R0 is 0 ohm. Your output resistance is 0. So these things they can ask for ideal op-amp, but now we are going to calculate the same thing for non-ideal case. So in non-ideal case, we will have everything R in, gain, voltage gain and R0. So let's calculate all the things for non-ideal case. Right, so we will have here, we will have R in. This node is grounded. अरे यार, this node is VD. From this negative node, there is RF connected. There is RF connected that is going outside of the op-amp, and it is connected to V node. Okay, so A into VD, this is the gain. So this is the way to represent our op-amp. Now we are going to calculate all the parameters, voltage gain and all those things. Now that will be a bit complex. Okay, the calculation will be a bit complex, but it is very important with respect to the examination. Right, so this is what we are getting. Now let's just remove this VD for now. Okay, so your target is to calculate V node by V in. Again, the assumption I am going to make is Rin is infinity. If I am calculating V node, Rin is infinity and R naught is 0. These are the assumption I am taking. Let Rin is infinity and R naught is 0. What will be the potential of this node? This was your V positive, this was your V negative. If you know the potential of this node, let's just say this node is V. So what will be, what you will write here? A into what is VD? Positive node is at 0, negative node is at V. So minus AV, and that is directly going towards V naught. So V naught is directly equals to minus AV. So you just need to write down the potential of V. What is V? V is R upon R plus RF into V naught. V is beta V naught. Is that so? No, because V in is connected. No, V in is connected here. So what is the scene for V? What is the scene? This is your R, this is your V in, this is your RF. The other node of RF is connected to V naught. This node is your V. So what will be the potential of this node? You can apply the concept of nodal as well. You can apply the nodal analysis here. V minus V in by R plus V minus V naught by R. V minus V in by R plus V minus V naught by RF actually is equals to 0. So from here also you will get the value, or there is one thing that I have told you hundred of times when I was teaching network analysis, when I am teaching analog electronics, there is one thing that I told you, one potential, other potential, one resistance, other resistance. So what is the potential of middle point? That is V in into RF, V in into this resistance plus V naught into this resistance plus V naught into R divided by R plus RF is equals to V. Say yes or no. Did I tell you this? Yeah. A lot of time I have told you this. What is the potential V? V in into RF plus V naught into R divided by RF plus R. So this is your potential V. So by equation 1, V naught is minus A into V in into RF plus V naught into R divided by R plus RF. So this R plus RF into V naught is going here, minus A into RF V in is going here, minus A into R V naught is going here. This I am getting is R plus RF plus A into R minus A into RF into V in. So V naught by V in. What will be V naught by V in? That would be minus A into RF divided by RF into 1 plus A into R. That's it. This is what you are getting. So in the examination, they can give you the value of A, RF and R, and then they can ask you the voltage gain. Are you getting this point? They can ask you the voltage gain in the examination. They can give you the value of A. They will not say that your OpAmp is ideal. Your OpAmp is ideal. They will just say that your OpAmp is ideal, but your gain is A equals to 10 to the power 3 volt per volt. So this you don't need to mug up. There in the examination you need to derive it. So I would recommend to do the derivation, not to mug it up. If you are mugging it up, that will be very difficult to minus A into RF upon RF plus 1 into RF plus 1 plus A into R. This is very difficult to mug up. So I highly recommend to derive it in the examination. It will be very, very easy. This node you can derive. You will have the value of V in, you will have the value of R, you will have the value of RF. This node you can derive. Simply this node into A and then minus sign will be equals to V naught. That's it. This node into A and then minus sign would be equals to V naught. That's it. And here in this case, if A was infinity, if A was infinity, then what would have happened? V naught by V in. Since A is very large, then this value will be very large, right? This value will be very large. So RF you can ignore, and 1 plus A can be replaced with A only. If A is very large, 1 plus A can be replaced with A only because 1 can be neglected, and this value is very large, so RF can be ignored. So in the conclusion, you can just write it AR. That would be equals to minus RF by R. So if A is tending to infinity, then your gain is minus RF by R. This is what you got here. This is what you got, minus RF by R. So I highly recommend to remember this. But once you solve many problems, once you see many configuration of OpAmp, we will see hundred of problems in OpAmp. So there you will be able to remember it. So 0, 0 minus RF by R. That's it. This is 0. This is 0. So V in by R current is flowing here. That means the V naught by V in would be minus RF by R. So in case of inverting amplifier, what is your gain? Minus RF by R. And in case of non-inverting amplifier, what was the gain? Gain was 1 plus RF by R. What was the gain? 1 plus RF by R. Right? So I will add a page here and we will simply write this thing down because it is used again and again. So I will just make the configuration of OpAmp. Okay. I will just make the configuration of OpAmp and then we will just remember what is the gain. I better pause the video and then make it. Yeah, so these are the two configurations. So what is the voltage gain of the first configuration? V naught by V. What is the voltage gain? This is a non-inverting amplifier. So for non-inverting amplifier, the gain is 1 plus RF by R. right? So this is what you need to remember. For this one, V naught by V in, the gain is minus Rf by R. So it is always good to write all those things, because this is what you need to remember. Okay, so this is just a note. So where we were, yeah, so voltage gain we have calculated. So voltage gain we have calculated. Now we are going to calculate input resistance. So second thing we are going to calculate is input resistance. Now this input resistance will be very, very interesting. So I need to calculate the input resistance, right? My target is to find V in by I in. This is my target. Input resistance. Better I call it R in with feedback. Okay, R in with feedback. One thing I know here is that there is this R in involved. This R in is involved here. Tell me one thing, if the potential of this node is V, what will be the potential of this thing? It will be minus AV. Say yes or no. No doubt about it. Potential of this node is A, then this node will be minus AV. Can you think of something? Now there is something that should click in your mind. Miller's theorem. There is a node, there is an impedance. Two nodes of the impedance are at fixed potential. One is A, the other one is minus AV. So what is the scene here? What do you understand from here? That there is a block of gain minus A, and one node of this resistance, RF resistance, is connected to V, and the other node is minus AV. Then what you can do? You can apply the Miller's theorem. So towards node V, what you will see? Towards node V, this is the node V. What you will see? RF upon 1 plus A, and towards the other node, let's just call this node as V dash. Towards the other node V dash, what you will see? This resistance from V dash, that would be Rf upon 1 plus 1 by A. Do you remember it? For capacitance it is C into 1 plus A and C into 1 minus 1 plus 1 by A. But here it will be Rf upon 1 plus A and Rf upon 1 plus 1 by A. Why it is plus? Because the gain is negative. The gain A is negative. Actually the formula is Rf upon 1 minus 1 by the gain. But the gain is minus A. Gain is minus A. So in place of this gain, I am writing minus A. So this minus minus will be plus only. So Rf upon 1 plus A. So this is what is happening. So at the input side you have Rf upon 1 plus A. So this Rf can be broken into two parts. Rf upon 1 plus A, and at the other side it will be Rf upon 1 plus 1 by A. But you need to see the input impedance only. So what you can see here is that this particular circuit can be broken into two parts. Can be broken something like this. This is your R, this is your V in. At the input side, what you will see? That would be Rf upon 1 plus A, and in parallel to that there is R in connected. The other node is grounded. The other node is grounded. Now whatever the VD potential is here, that is of no use. Whatever the VD potential is there, that will be amplified. VD potential will be amplified with the factor of A. Then you are having a R naught, and from that R naught you are getting this Rf upon 1 plus 1 by A. Say yes or no. Right? And this is your V naught. But you don't need to think of this side. You just need to tell the resistance from here. This is your R in with feedback. R in with feedback. This is your R in with feedback. This I will close in a box. So we have applied the Miller's theorem here. So this is what we understood. We applied the Miller's theorem. When we applied the Miller's theorem, this RF here it was coming out to be RF upon 1 plus A. And in parallel to that there is R in. So what is your R in feedback? R in with feedback. R in with feedback. So what is your R in with feedback? That is R plus RF upon 1 plus A in parallel to R in. This is your final answer. So in the examination, these kind of questions are asked. Even in the interview, these kind of questions are asked. So they will check if you are going to apply the Miller's theorem or not. This node is V, this node is minus AV. So R plus this parallel resistance. I hope you have understood how I wrote this input resistance. That is R plus parallel of these two. RF plus 1 upon A, RF upon 1 plus A parallel with R in plus R. So R is in series with this configuration, and this configuration is R in parallel with RF upon 1 plus A. So R in with feedback. This is the input resistance. Well and good. Understood? Everything is crystal clear. Now we are going to calculate output resistance. So in input resistance, we reduced the calculation. We did something smart. What was the smart thing we did? That we took RF to input side. If we are taking RF to the input side, output side we don't need to see because we are just calculating the input resistance. So we took it to the input side. So R in parallel with RF upon 1 plus A plus R. That's it. Now we are going to calculate output resistance. So the third thing I am going to calculate is output resistance. So let's see what do we need for output resistance. I don't think we will be needing this diagram, so I can cut it off. What is the first thing we do for output resistance? That is short circuit this. That's it. This is shorted. The other thing is that in output expression I don't need R in, so I will take R in to be infinity only. R in to be infinity. Certainly this VD node will be used. So this is the assumption I will take. So if I am calculating R naught with feedback I am writing, so that would be V naught by I naught. So my target is to find V naught by I naught. This is my target, right? This is my target. This is what I need to find. So what will be the potential of this node? What will be the potential of this node? Let's just call this node as V. If this node is V, then this node will be minus AV, right? Because this node is grounded, this node is minus AV. So again, the assumption that I am taking is that the complete I node is flowing through R node only. So what is the assumption? R naught is too small, so it takes all the I naught current. All the I naught current. So my target is to find V naught by I naught. So what I can write? V naught minus of AV. This node is minus AV. V naught minus of AV divided by R naught is equals to I naught. So V naught plus AV is equals to I naught R naught. What is your V? What is your V? V is R upon R plus RF, R upon R plus RF into V naught is equals to I naught R naught. Say yes or no, right? So what will be your V naught by R naught? V naught by I naught. That would be R naught upon 1 plus AR upon R plus RF. That's it. This is your R naught. 1 plus AR upon R plus RF. So R naught is not that important, but the important part is this Rin. So in Rin, we smartly apply the Miller's theorem and reduce our calculation. And in R naught also, the assumption is that the complete current is flowing through R naught only. So V naught plus AV divided by R naught is equals to I naught. So I just need to replace the V, and V I can replace very easily because Rin I am considering infinity. Rin I am considering to be very large. So V will be simply R upon R plus RF into V naught. From there I calculated V naught by I naught, that is R naught upon 1 plus AR upon R plus RF. So this is your R naught with feedback. I should have written R naught with feedback. This is your R naught with feedback. So this is the analysis we have done. Complete analysis we have done for inverting and non-inverting amplifier. Now what is the thing that is remaining? That is that now we are going to understand this with the concept of feedback topology. So understanding non-inverting amplifier with the concept of feedback topology. So this I am going to write down. Understanding, sorry, inverting amplifier, not non-inverting amplifier. Understanding inverting amplifier with the concept of feedback topology. Now this will be very interesting and will not be that much straightforward. Okay, so get your whole concentration for next 15 to 20 minutes and you will be able to understand it. Okay, but keep your whole concentration, otherwise you will be forgetting everything. First tell me what kind of feedback topology is there. What kind of feedback topology is there? Let's talk about mixing. This is input current IN. It certainly has two paths. One path to go here, other path to go here. Certainly has two paths. Current mixing is there. Now no one will say, sir, there is 0 ampere current, so it will go from here only. Yeah, I told you this when I was teaching you feedback topology in MOSFETs. So what did I say? That even if it is a 0 ampere current, but still it will be considered as a path only. This path and then this path. Because what if this OpAmp is not ideal? If it is non-ideal, it can drive some current. So it will be considered as a two path only. One path in RF, one path in the OpAmp. So it has two paths. So current mixing is there. What about sampling? So what is the method of sampling? Simple method of sampling is that you just put V naught equals to 0. If you put V naught equals to 0, is there anything coming at the feedback path? Is there anything coming in the feedback path? No, there is nothing coming in the feedback path. If I put V naught equals to 0, there is nothing that would come into the feedback path, right? Because the current has to mix now. One thing I know is that there is current mixing. So this is your I in. Some feedback current should come. If your V naught is 0, there is no chance that feedback current would come because this node is this node is 0 only, nearly equals to 0 only because of virtual short. If this is 0, this is 0, there will not be any feedback current coming. So certainly there has to be voltage mixing. Sorry, not voltage mixing, voltage sampling. So there is voltage sampling and current mixing. So what kind of feedback topology is that? Voltage current. Voltage current feedback topology. There is voltage current feedback topology. If there is voltage current feedback topology, tell me one thing. If there is voltage current feedback topology, so what kind of amplifier is that? Output is voltage, input is current. That means it is transresistance amplifier. Transresistance amplifier. And how do you show a transresistance amplifier? The input is current. So how do you show it? that your input is current, that will be mixed. There is this input current that will have the gain that is equals to Rm, right? Input current, it will be multiplied with Rm. Forward gain will be Rm. It has the unit of ohm, and you will get an output equals to voltage. Listen to me very carefully. Look, this is a transresistance amplifier. Input current that will be multiplied with Rm, not A. Not A. Now, A is volt per volt or current by current. But input current will be multiplied with Rm and will generate voltage V. Voltage V naught. So In into Rm is equals to V naught. So this has a unit of ohm. Okay, so this is not this A, this node, this A that you see, that is for voltage amplifier. So this particular configuration is voltage amplifier, but this complete configuration is trans resistance amplifier. Are you getting this point? Right? This is Rm and this is your V naught. Now it is fed back towards the input side. That will be multiplied with Gm. This is In. If there is negative feedback, certainly there is negative feedback, so If would be coming, and here In minus If would be going. What you would write here? Here you would write Gm. So V naught will be multiplied with Gm and you will generate If. So In minus If will be going towards Rm and you will get V naught out of it. Say yes or no. Is that clear? This is the block diagram. So now you cannot write that, sir, what will be your voltage gain? Voltage gain will be, sir, A upon 1 plus A beta. Now, your voltage gain will be Rm upon 1 plus Gm Rm. This will be your voltage gain. But now you don't know the value of Rm and Gm. In the previous case, you know the value of A and beta. That was directly seen. That A and beta was directly seen. But here Rm and Gm are not directly seen. You have to calculate it. So let's just frame a question out of it and then try to make the block diagram of this particular configuration like this. Our target is to make that block diagram of this particular configuration like this. So this is our target, right? So I will frame a question out of it. How will I frame it? So what I will do, this particular configuration is represented like this. Copy and paste. And to make it, I will remove all those things. I will remove it. We'll remove this one as well. What I will do, this is my V in. This is my V in. And this is some alpha. This is Rm, this is Gm, this is your V naught. So this particular configuration that OpAmp is given, this is a question. This is represented like this. Now you need to tell the value of alpha, Rm and Gm. So find alpha, Rm and Gm. This is the task. Do this question on your own. Try to do it on your own. You need to make it as a trans resistance amplifier. What you will do? This V in, this is R. So what I can do is that I can replace this voltage source as a current source. Say yes or no. This was the voltage source. I replaced it with the current source. The current is V in by R and this resistance is R. That is directly connected to an op-amp. And your output is here, output is V naught. What kind of feedback topology was there? Voltage current. Voltage current. So for voltage current feedback topology, what do I know? That my Rin is low. Say yes or no. Voltage current, Rin should be low and Rout also should be low because it will be converted into voltage, so Rout should be also low. This we have already studied in feedback topology. I hope you have completed the feedback topology, then only you are watching this lecture. So for voltage current feedback topology, Rin should be low because input is current. So you want more and more current to go into Rin. You want more and more current to go into Rin. So that means Rin has to be low and Rout should also be low. Why is it so? Because your output is voltage, so you want more and more voltage to go towards the load. So Rout should also be low. So if Rin is low, what I can do? This potential, whatever the potential I will have, let's just say this potential is some Vx. That will be low only because Rin is low. The voltage across the current source will be low. Why so? Because Rin is low. So I can nearly consider it to be ground. I can nearly consider it to be ground. Say yes or no. If Rin is low, I can nearly consider it to be ground because Vx is going to be low. So from output, what is the current coming? That is V naught by Rf. This is your I in current that is coming V in by R. And since this is grounded, so R will not eat up any current. So the current will go like this. V in by R plus V naught by Rf is current is going. But I need V in by R minus some current. Minus some current I need because here there is minus. So what I will do, I will take the direction to be opposite. I will take the direction to be opposite. This direction I will take and the value of current is V naught by Rf. Are you getting this point? I am taking this as my feedback current. This as my feedback current. This is my feedback current and this is my input current. This is my input current. This is my input current. And where the current will go? The current will go into transresistance amplifier. The current will go into transresistance amplifier. The current will not go into voltage amplifier. This is the voltage amplifier. So my task is not to find this current. My task is to find the current into the transresistance amplifier. That's it. So first let's write down what did we understood. We understood that my I feedback is V naught by minus V naught by Rf because I feedback value is minus V naught by Rf. So what is my GM? GM is IF by V naught only. GM is IF by V naught because this will be my IF, right? So IF by V naught, that would be equals to minus 1 by Rf. So first thing I have found, that is my GM, that is minus 1 by Rf. That's it. So GM I have found. One more thing I have found. What is my input? What is my input? This is my input. What will be that? So alpha V in is equals to I in. And here it is given that I in is equals to V in by R. So that, what do you understand by that? It is given I in is equals to V in by R. The input current is V in by R. So what do you understand by that? That your alpha is 1 by R. Alpha is 1 by R. This is your alpha. Right? I in is input current is V in by R and alpha V in is equals to I in only. So alpha value is 1 by R and GM value is also there. Now you need to calculate Rm. You need to calculate Rm. So what is the easiest way to calculate Rm? That can be, let's consider this block diagram into open loop. Let's consider this block diagram into open loop. So let's make open loop. If I make open loop, what will happen? This was my I in here. There is no feedback coming. The feedback coming is 0. I don't need to think about feedback. Then there is this feedback this factor Rm is there. And then you are having a output. This is your output V naught. That's it. So simply I in into Rm is equals to V naught, right? Because there is 0 current coming here. So I in into Rm is equals to V naught. This is the open loop. Now I can make the open loop for this configuration as well. So this I will simply copy, right? This is of no use, and this will be open loop. So this feedback path is gone. Now what is the scene? This is your I in. This is your I in. This is your I in. There will be 0 ampere current here, right? So this complete I in will be flowing through this resistance R. So if it is flowing through this resistance R, there will be some voltage drop here. What will be that voltage drop? This voltage drop will be I in into R. Now that voltage drop will be multiplied with the factor of A. And minus sign will be equals to V naught. Whatever the voltage drop, let's just say the voltage drop is V here. That V voltage drop is I in into R. And that will be multiplied with A. And since this is negative terminal, so 0 minus this potential into A is equals to V naught. 0 minus this potential, let's just call this potential as V. So what will be my potential V? My potential V will be I in into R, right? And what is my V naught? V naught is minus AV. So minus A into what is my V? V is I in into R. So what is my V naught by I in? Here my V naught by I in is minus A into R, and that is equals to Rm. This is equals to Rm. So this is the value of your Rm. This is the value of Rm, that is minus AR. This was the value of Gm. This was the value of alpha. So now you can replace this diagram, or you can copy this complete diagram, complete structure you can copy. You can tell them that, sir, if you are considering feedback topologies, then my circuit roughly I can, okay, this will be I in only, this is Rm, this is Gm. So V in divided by R is my I in. Then it will be multiplied with the factor of minus AR. From output, the feedback fed is minus 1 by RF. That's it. So this is the block diagram. So these kind of questions are asked in a very good interview. So if these kind of questions people are asking you in the interview, then consider that you are going to be selected, because that's why he is asking you these kind of questions, because he is very impressed by your analysis. So he must have asked you about MOSFETs, OpAmp, and simple RCRL circuits. But if he is asking you these kind of problems, that what kind of amplifier is that, if he is going deeper into feedback topology, that means he is very much interested in hiring you. Or in the gate examination as well, these kind of questions can come that they can ask you what will be the rough value of alpha, Rm, and Gm. So this OpAmp is made into a block diagram, and then they will ask you these values, because in the gate examination it is since 2016 I don't see any question is there from feedback topology. So certainly one question is coming from feedback topology, and that will be very, very interesting. So now they are going to frame a very good question from feedback topology, and I highly believe that the question will be from inverting amplifier, because inverting amplifier is very interesting to study, because that is a trans-resistance amplifier. The OpAmp is voltage amplifier. The complete structure is a trans-resistance amplifier. So what did we studied? That it is a trans-resistance amplifier Then I can replace it. I in from output, there is a feedback current is coming, that is being multiplied with RM resistance, forward resistance, that is multiplied with the forward resistance, and you are getting a V0 output voltage. So this is how you can replace it. Then your task is to find alpha, RM and GM. Then this voltage source you converted into current source. This is the first task this is what you did. Then slowly we move towards the problem. So first we found the feedback factor. So what was the feedback factor? Feedback factor was minus V0 by RF. Why it was minus V0 by RF? Why it is not V0 by RF? Because I needed the current to subtract. I needed current to be subtracted. If IF is coming in this side, IN is coming in this side, then both will be added. But I wanted current to be subtracted. So IN minus IF I wanted. So that's why I took opposite direction. So that is minus V0 by RF. So GM is minus 1 by RF. And what about our alpha? So alpha is here, there is simply current. So alpha will be 1 by R only. Right? And then my target was to find RM. So how did I find RM? So I made the open loop. When I made the open loop, IN was there. There is no current coming from the feedback. So IN into RM is equals to V0. So if I make the open loop in this configuration as well, so simply IN into R into minus A is equals to V0. That means what is the value of V0 by IN? V0 by IN is equals to RM. So V0 by IN is minus A into R. So this is my forward gain. So this is how I can replace it. Are you getting this point? So I hope you have understood the concept of feedback topology. Here you have understood the concept of inverting amplifier, non-inverting amplifier. So quickly revise this chapter, quickly revise this 1.5 hour, whatever that we have studied. So you will be understanding a lot new things, even if you have studied it previously, because I know no one teaches in that depth manner. Okay, so yeah, I know this thing, but I hope you have understood a lot of new things. Right, so first we saw voltage gain, current gain, and then inverting amplifier we saw input resistance, output resistance we saw. Then we saw the voltage gain for the inverting amplifier, but for non-ideal case. That was very interesting point, that we need to find voltage V here. That was V in into RF plus V0 by R upon R plus RF. So we found V0 by V in. Then we found the input resistance. So input resistance, we smartly did one thing. What was that thing? That RF upon 1 plus A we took, right? And yeah, one more thing you can say here is that if you took ideal case, if A is infinity, then what will happen? This resistance will be 0, right? Anything parallel to 0 will be 0 only. So you will get R only. What I am saying, if your A was infinity, then what was the input resistance you get? If A was infinity, what was the input resistance you were getting? R. If A was infinity, the input resistance was R only. In this expression also you are getting the same thing. In which expression? In this expression. If you put A equals to infinity, this will be 0. 0 parallel with any resistance will be 0 only. So R plus 0 will be R only. Right? So this also you can check here. Then we calculated output resistance as well. This resistance we calculated output. So what was the output resistance you got for ideal case? It was 0. For ideal case it was 0 ohm. For ideal case it was 0 ohm. If you put R equals to infinity here, if you put A equals to infinity here, if you put A equals to infinity, this will be equals to 0 only. If A is equals to infinity, what will happen? Your R0 with feedback will be equals to 0 ohm only. Okay. So this also you can check here. Well and good. Then we understood the concept of feedback topology here. That the topology is voltage current feedback topology. Okay. So what did we understood? We found the value of alpha, RM and GM. Okay. There was current mixing and voltage sampling. So the feedback topology was voltage current feedback topology, and it was a transresistance amplifier. For transresistance amplifier, both R in and R out are low. From there we found the value of alpha, GM and RM. That's it. So this was a complete lecture. I hope you have found this lecture helpful. Okay, let's meet in the next lecture. We will study a lot more new things. We will study voltage followers, then we will see adder using OpAmp, then we will see subtractor using OpAmp, then we will see differential amplifier, we will see instrumentation amplifiers. So all these kind of things we will see using OpAmp. Okay, then let's meet in the next lecture.